This is AP Chemistry Podcast 1.2. We're going to talk about matter, how it's classified, and then we're going to talk about nomenclature, so naming compounds. We'll do ionics, covalents, and acids. And then we'll do balancing equations and some stoichiometry. So we have a lot to do. All right, quick definition. Matter is anything that has mass and takes up space. You can see the representation here of solids, liquids, and gases. This is what we usually talk about when we talk about the three states of matter. Normally not plasma because we don't experience it much. So you can see with the solid, they're arranged in a certain pattern. They're very structured. They're packed tightly together. The liquid, they're flowing around each other. And then with the gas, there's a lot of space between them and they're moving really, really quickly. So if we look at this, you need to remember a homogeneous mixture, and mixtures are anything that have a variable composition. A quick definition or a quick way to tell is there's no chemical formula. So a mixture, any ratio of compounds put together. If it's homogeneous, it's the same throughout. That also means that you'll probably only see one phase. So maybe it's all solid, it could be an all liquid, all gas. Examples of homogeneous mixtures would be air, salt water. You could say juice, maybe apple juice. Although if you get into juices and you think of maybe orange juice with a pulp, that would be heterogeneous. So we're talking juice with no pulp, more like apple juice. So those are three good examples of a homogeneous solution. You may also remember briefly talking about alloys. Alloys are a type of homogeneous solution. Alloys are things like brass. These are a mixture of metals. So those are also considered homogeneous solutions, mixtures. Heterogeneous, then, if this is the same throughout, this is not the same throughout. There is only, there's two phases or more. And examples that we could think of might be pop. So if you think of pop that is still carbonated, that would be heterogeneous because you have the liquid, which is the pop, and then you have the carbonation, which is the gas. So two phases make that a heterogeneous. Cereal, granite, rock, anything you can see different parts in would make it heterogeneous. Pure substances are on the other side of matter, so we have mixtures in matter. If these have no chemical formula, that means a pure substance does have a chemical formula. Oops, I can spell. So chemical formula. Pure substances can be split into elements, into compounds. Elements you find on the periodic table. Compounds are also from the periodic table, except there's more than one type of element that make them up. So an element might be hydrogen gas, because there's only one type of atom, just hydrogen atoms. Compound would be water. So elements, if we break those down even further, you can go to your individual atoms. Atoms have their nucleus in the center and electrons around the outside. And then electrons, or the nucleus, can be broken down into protons and neutrons. You need to remember that electrons are negative. In the nucleus, the protons are positive. The neutrons have no charge. And then even farther from those, you can break them down into quarks. So this kind of gives you the whole breakdown of matter. Make sure that you remember how to categorize and classify matter. All right, if we want to separate mixtures, so we're talking about the left side of that table we were just looking at. There's three different ways we can do that. The first way is through distillation. Distillation uses the idea of different boiling points. And in this case, in our flask here, we have salt water. So they're trying to purify the salt water so that it's just water and it's drinkable. So what you would do is you take your sample of whatever you're trying to purify and you're going to heat it with a Bunsen burner. That's going to cause just the water to vaporize. So as the water vaporizes, it's going to leave the salt alone down here. So the water vaporizes, it travels into this tube, and in order to get it to condense again, they run cold water around this tube where that water vapor is running. And the cold water drops the temperature, causes it to condense, and then you can collect it in this flask down here. So we have the salt water, the water vaporizes, travels, condenses, and then we can collect it here. This is your distilled water. So distillation is a way that you can separate mixtures using the different boiling points of the substances that you have. Then we have chromatography. Chromatography, I'm pretty sure everybody's done, and this is the common example where you have your piece of chromatography paper. You put the ink spot or the marker spot, whatever you have, at the very bottom, and then you just drop it into your solution. In this case, it's water. It needs to be right above it. Then the water is going to travel its way up the paper. So it gets pulled up by its attraction to the paper, and as it does that, it causes it to separate out. So it takes the ink with it, and as it goes, you can see it start to separate out into all the colors that make it up. And then the third way is through filtration. And filtration is another really simple process that everybody's done. You have the funnel with the filter paper, and then you have your solution right here. In your solution that you're trying to separate, there's usually a solid and a liquid. So in here you're going to have some solid particles that you're trying to separate out from the liquid. And when you do that, you dump it down a glass stir rod, and the reason you do that is for a more controlled pour. You don't want it to run down the beaker here. So the glass rod helps you make sure it gets right into the funnel. The solid gets trapped in the filter paper, and then the liquid makes its way out. We call that the filtrate once it comes out. So filtration is the third way that you can separate components of a mixture. All right, that was it for classifying matter, so on to nomenclature. We're going to start with naming ionic compounds, and if you do not have your periodic table out yet, you should go grab it. Rules for naming ionic compounds. You want to name the cation. The cation is normally a metal, so if it's a metal, you're not going to change anything about the name. If it's a polyatomic ion, you're not going to change anything about the name either. So the first part of an ionic compound, you just call it what it is. Whatever that cation or that positive charge is, it doesn't change. Then you need to make sure that you check if you need a Roman numeral. Transition metals, so copper, lead, iron, all of those you're going to have to identify what the charge was that you used. And you do that with your Roman numerals. And then you have the anion, and the anion is the negative part of the ionic compound. It always comes last. If it's a non-metal anion, so chlorine, you change it to chloride. Fluorine would become fluoride. Iodine would become iodide. So all the nonmetals get the ending "ide." If it's a polyatomic ion, you don't change anything about it. It keeps the name. So if it's carbonate, it stays carbonate. You don't change it. So we're going to try a few. All right, here's our examples. Remember, with ionic compounds, we need to balance charges when we're writing them. We need to have the positives balance the negatives. So on your periodic table, if you look and you find gallium, gallium is going to have a +3 charge. And then iodide is really iodine, and we find it over there in the halogens, and it has a -1 charge. So to get a +3 and a -1 to balance, I need 3 of the iodines. So that would be GaI3. Chromium. Chromium is Cr, and in this case, I don't even have to look it up because there's a Roman numeral that tells me that it is a +3. Chloride is chlorine. It's in the same family as iodine, so I know it's a -1. And when I write this, same way here, I'm going to need 3 of the -1s to balance out the +3. So this is going to be CrCl3. Sodium. Sodium is over there in the alkali metals. It's a +1. Hydrogen carbonate. Remember this one from the first day quiz. Hydrogen carbonate and bicarbonate are the same thing. So that's the HCO3, and it has a -1 charge. So sodium has a +1, bicarbonate is a -1. I'm just going to smash them together because they cancel each other out. This is the fancy way of saying baking soda. Sodium hypochlorite. Sodium is a +1, and then if you remember your polyatomics, or maybe you have to go back and look, hypochlorite is a -1, and it's ClO. That hypo means it has the least number of oxygens. So if we put these together, we have a +1 and a -1. So we have NaClO, and that's it. Let's see, let's refresh really quick. We can have perchlorate, these rules. We can have chlorate, we can have chlorite, and we can have hypochlorite. So when you're looking at these endings and the beginnings here, they kind of give you clues. Per means the most oxygens. So perchlorate is going to be ClO, and there's going to be 4 of them with a -1 charge. Chlorate has 1 less, so it's ClO3 with a -1 charge. And then chlorite is even less, so ClO2 with a -1. And then hypo means you have the least number of oxygens, so it's ClO. So perchlorate is 4, just chlorate 3, chlorite 2, hypochlorite is just the 1 oxygen. And that kind of works the same if you're thinking of nitrate and nitrite. If you can pay attention to those endings, they kind of clue you in and you can figure it out. So you have your nitrate, which is the negative, the NO3 with a negative charge, and nitrate or nitrite is 1 less, so it's NO2 with a -1 charge. If you can kind of realize the pattern that follows those along, it'll help you with the polyatomics. So back to this. Iron 2, they're telling me it's iron with a +2 charge. Nitrate, we just said, is a -1. So this is going to be Fe, and I need 2 of the nitrates. And because this is a polyatomic ion and I need more than 1 of them, I need to remember parentheses around this. And then the very last one here, potassium, same family as sodium, it's a +1, and bromate is a -1. It's that BrO3. Since it's a +1 and a -1, it's KBrO3. So those are just a few to get your mind back into the naming game. Let's try the other way. So now we want to go from the formula back to the name. The only thing we need to watch out for here is if it's a transition metal, or then I don't need to worry about charges. But if it's a transition metal, I need to pay attention so I can do Roman numerals. So we look at this first one, cobalt. Cobalt is a transition metal. It can have more than 1 charge. So I'm going to have to put in a Roman numeral. So I'm going to go cobalt. I'll leave room to come back. And bromine becomes bromide. In order to figure out the charge on this cobalt, I look at what it's attached to. So bromine has a -1 charge, and I have 2 of them, which means overall this is a -2. To balance that out, that must mean that this one cobalt is a +2. So this would be cobalt to bromide. Calcium. Calcium is not a transition metal. That means I do not need to worry about Roman numerals. And then Cl is chlorine, and we change it to chloride. You do not get to get dots on the eyes. It doesn't want to do it. All right, aluminum. Aluminum is not a transition metal. It cannot have more than one charge. That means that this is aluminum. I do not need a Roman numeral. And oxide. Sodium, again, sodium not a transition metal. But remembering my polyatomics for the second part, SO4 is sulfate. And because it's a polyatomic, I do not change the name of the polyatomic ion. It stays as it is. Mn, be careful with this that you don't call it magnesium. That is manganese. Manganese can have more than one charge, so I need some Roman numerals with that. OH is hydroxide, another polyatomic that we use quite a bit. So let's go back here and figure out what manganese has for a charge. Think about it in halves here. Hydroxide is a -1 and I have 2 of them, so this side has a total charge of -2. Since I only have one manganese, it must be a +2. So this would be manganese 2 hydroxide. And the last one here is iron. This iron is a transition metal. It can have multiple charges. We'll put in our parentheses for a Roman numeral. NO3 is nitrate. And if I go back to find out the charge, nitrate is a -1. I have 3 of them, so this side has a total -3 charge. This iron has to balance it out, so it's a +3. That makes this iron 3 nitrate. Okay, moving on. The next one is covalent compounds. So covalents seem to be everybody's favorite. They seem to be a little easier. All you have to remember are the prefixes. You name the first element, and the only thing with this is you do not use the prefix mono on the first element. Sometimes you never see anybody use mono at all. It just kind of depends. But this is the key thing you need to remember is do not use mono when we're talking about the first element here. When you're naming the second element, it's just like doing the ionics. You want to change the ending to "ide." So if it's chlorine, it becomes chloride again, just like when we were doing ionics. And for the second element, we want to use prefixes to tell how many, and it's okay to use mono on this one. So I can't remember if you have these written or not in your handout. If you don't, you should pause it and write them down. These are all your prefixes 1 through 10. They're the only ones you'll need. Mono, di, tri, tetra, penta, and so on. Remember when we're plugging these into names, the last vowel, the A here, will get dropped if you're attaching it to an element that begins with a vowel sometimes. It just depends on what it is. You just kind of got to watch out for that. So here we go. We're going to practice both ways again. We'll start going from the names to the formula, and then we'll go from the formulas back to the name. So sulfur, it's not monosulfur because we don't use mono, but just because it's the regular sulfur, it tells me that there's only one, so it's S. Hexa is the prefix for 6. So I have hexafluoride, so it'd be F6. These are fun and easy because they tell you exactly how many to do. Sulfur again, no prefix, just an S. Tri is 3. Oxide is oxygen, so this would be SO3. People want to call this sulfite. Now this is not sulfite because sulfite has a charge. Sulfite is SO3 with a 2- charge. This is just SO3. So SO3 does not equal the sulfite ion. Don't get those confused. Carbon. Carbon with no prefix tells me there's just one. Di, meaning 2. So this is CO2. Dinitrogen. 2 nitrogens. There's that mono. So this is dinitrogen monoxide 1O. There's your examples. Those shouldn't be too bad. So rules for naming acids. You want to really just focus on the anion. All of our acids begin with hydrogens, so we don't really consider that. It's just the anion that helps us name it. So if the anion is an element, we have hydrogen attached to some element. That is when we use the word hydro. So if it's hydrogen attached to an element, that's when we get to use the prefix hydro there. So it's hydro something ic acid. We'll do some examples with these two. So element and hydrogen, you get to use that hydro and it's the ic ending. If the anion ends in ate, so maybe sulfate or nitrate or phosphate, then the acid is blank ic. So the ending ate becomes ic. Remember, I ate something icky. So sulfate becomes sulfuric, or phosphate becomes phosphoric. You take that element and you add the ic on it. If the ending is ite, so ite becomes os. Nitrite would become nitrous acid. And that's just a rule that you're going to have to remember. Notice though, because it's not an element attached to the hydrogen, it's going to be a polyatomic, that you don't get hydro there. So hydro is reserved only for an element attached to a hydrogen. All right, here's some examples that we have. So from the rules, if we see this word hydro, that cues us in that there's just an element attached to a hydrogen. So we have hydrogen attached to chloric would be chlorine, and you do need to balance charges. Hydrogen is a +1, chlorine is a -1. They balance each other out, so it's just HCl. And that one you probably knew off the top of your head. Chloric, so this was hydrochloric and this is chloric acid. Chloric comes from chlorate, and we know chlorate, so I have a hydrogen which is a +1. Chlorate is the ClO4, no it's not, that's perchlorate. Chlorate is ClO3 with a -1 charge. So chloric acid would be HClO3. Acetic acid. Acetic, no hydro, so ic came from ate, so this comes from the acetate anion. We have our hydrogen, and we're going to smash it together with the acetate anion. +1, -1, it's HC2H3O2. Sometimes this is the one that you see written as CH3COOH. So you can see it both ways on that one. Nitrous. Us comes from ite, so this is the nitrite anion. We have a hydrogen attached to the nitrite anion, and since it's +1, -1, it's just HNO2. Perchloric, which I tried to do up here, perchloric comes from perchlorate, and that is the ClO4 with the minus charge. So this is HClO4. So the hydro is your clue whether it's an element or a polyatomic ion, and then the endings of the others, the ic is the ate, and the OUS is from the ite. Key thing there. All right, let's go the opposite way. If I'm looking at this one, this is hydrogen attached to an element, which means I need the prefix hydro, and fluorine becomes fluoric. So that's hydrofluoric acid. This is not an element, so I do not use hydro. This is the nitrate anion. And since it's nitrate, it's going to be nitric. So this is nitric maybe, nitric acid. All right, this is the sulfite anion. I'm not going to use hydro because this is a polyatomic ion. So since this is sulfite, this would be sulfurous acid. This is an element, bromine. I'm going to quickly write hydro as the prefix. Br is bromine, and it would become bromic. And then the last one here, ClO2, is chlorite. That means that ite becomes the ose. So this is chlorous acid. All right, when we are balancing chemical equations, we are obeying the law of conservation of mass. That's the law that says you can't create mass or you can't destroy it during a chemical reaction. So what we have at the beginning means we have to have the same amount at the end. That means atoms are just rearranged, and we already know this. So if we look at an example here, we're taking methane, which is CH4, so I have my one carbon, the carbon's right in the middle. All these guys around here are my hydrogens. And if I check this, I have methane reacting with oxygens, so there's my O's, and I get CO2 and I get H2O. And since this is correctly balanced, I've got my coefficients right here, that means that if I look on both sides of the reaction, I have 4 hydrogens, I have 4 hydrogens. I have a carbon and a carbon. There are 4 O's here, and I have 4 O's there. So what I have on one side has to be what I end up with on the other side. And this is why we balance equations. So here we go with some practice ones. C6H12O6 is combusting. When you're doing a combustion problem, so combustion problems, you want to begin with the carbons and the hydrogens. You want to leave the oxygens for last because they are all by themselves right here, so it makes it a little easier if you leave them until the last place. So we'll start with carbons. I have 6 carbons on this side. I need to have 6. There's only 1. So I'm going to throw a 6 out there for the coefficient. I'm not going to worry about oxygens at the moment. I'm going to go back and do hydrogens. So I have 12 hydrogens. I need to have 12 on this side. 2 times 6, so I need 6, gives me 12 hydrogens. Now I can focus on the oxygens. So 6 times 2 is 12 oxygens, plus 6 times 1 is another 6. So I have a total of 18 oxygens on this side. I need to have 18 oxygens over here. Well, there's 6 here that I already have and I don't really want to change. So 18 take away 6 is 12. That means I only need to make 12 here in order to get the 18 that I need. So 12, there's 2, so I'm going to have to put a 6. And this is 1, or you can just leave it blank, but I'll go ahead and just put a 1. So that gives me 6 carbons, 12 hydrogens, 12 hydrogens. 6 plus the 12 O's is 18. And then 12 plus the 6 O's here is 18. So everything balances out with 1666. This one's simple. It's the synthesis of water. I'm going to start with the O's because the hydrogens are balanced. So I have 2 oxygens. I need to have 2 on this side. I'll put a 2. That changes my hydrogens though to 4. So I have to come back to this side and put a 2 here as well. So that ends up being 2, 1, 2. We'll do a couple more. Nitrogen and hydrogen gas react to give you ammonia. My hydrogens are 2 on this side and 3 on this side. 2 and 3 both go into 6, so that's what I'm going to try and do. Hydrogens 2, I need 3 to make 6. 3 times 2 is 6, and on this side I need to put a 2 here because 2 times 3 is 6 for those hydrogens. Nitrogens, I have 2 on this side And since I put that 2 there, I also have 2 on the product side. So everything matches up with 1, 3, 2. And for this last one here, I have 1 nitrogen on both sides, but I have 3 oxygens on this side and only 2 here. I don't like odd numbers like this, and I can make it even if I put a 2 out in front. So if I put a 2 there, it changes my oxygens to 2 plus 2 is 4. So if I want 4 on this side, I have to put a 2 out there. But that changes my nitrogens to 2, which is okay because now it matches this side with 2. So it should be 2, 1, 2 for the balanced equation. All right, stoichiometry. It's everybody's favorite. You always start with the balanced equation. That's why we just did that. So make sure that you can write a balanced equation. I like to write what I know underneath the chemical symbols so I can keep track of what I have and where I'm supposed to go. To do that, I write the given amount underneath the symbol in the equation, and then I put a question mark with the units for what I'm looking for. And then you just use your dimensional analysis. So you just use your little table that we were doing earlier, and you just do all your conversions to get whatever you need. Remember that you can use the coefficients from the balanced equations as the mole to mole ratio. That's how you can switch from one substance to another, is using that balanced equation. That's why it's so important. Important things that you need to remember when doing stoichiometry: relationships. 1 mole of anything has 6.02 times 10 to the 23rd things. So if I have a mole of pennies, I have 6.02 times 10 to the 23rd pennies. It's just, it's a number, it's a counting unit. When you're at STP, we know 1 mole of any gas has a volume of 22.4 liters, and that your coefficients in your balanced equation can be moles, liters, or individual molecules and atoms. It is really important to remember that your coefficients do not stand for mass. You cannot use those for grams. So here we go. We're going to do some practice. All right, here we go with our example. How many liters of hydrogen gas are formed when 13.5 grams of calcium react with sulfuric acid? So the first thing I need to do is make sure I have a balanced equation. They're saying that hydrogen gas is formed, so that is a product, and I need calcium reacting with sulfuric acid. So calcium reacts with, and then sulfuric acid. If we remember back to naming acids, the sulfuric comes from the sulfate anion, and then because it's an acid, there's a hydrogen. So we have hydrogen with a +1 charge and the sulfate with the 2-, which means when I put them together, I need to make sure I have 2 hydrogens to balance out the charge of the sulfate. Forms hydrogen gas, and hydrogen's diatomic, so you get H2. And there has to be something else because I haven't used the calcium or the sulfate yet. We can tell that this is a single replacement reaction. The calcium's going to come in, join with the sulfate, and it's going to kick the hydrogen out by itself. So that leaves me with calcium, which is a +2, sulfate, which is a -2, so it's just CaSO4. Balancing, everything balances on each side. It's just ones across the board. So I'm going to go in and I'm going to write what I know. I know I have 13.5 grams of calcium. And it's asking me how many liters of hydrogen gas. So liters, I do not know. And since it's not giving me a temperature or pressure or anything, I'm going to assume it's STP, so I can use that 22.4 liters. So I always have to start with what I'm given. And I'm going to make sure to label all the way through this so we can keep track of what we have. Straight in line as I can do. All right, I'm in grams. That's over 1. The first thing you need to do is molar mass to get to moles, because then I can use the balanced equation if I'm in moles. So on your periodic table, if you look up calcium, calcium is 40.08 grams. So 40 point, maybe, 0.8 grams is 1 mole of calcium. All right, perfect. Grams, grams, go away. I'm in moles. This is my chance to use the balanced equation. For every 1 mole of calcium that reacts we produce 1 mole of hydrogen gas. That's a good thing. Moles, calcium go away. And then I need to get to liters. So we said earlier that at STP, 1 mole of any gas is 22.4 liters. So that is the conversion factor I'm going to use now. 1 mole of hydrogen at STP is 22.4 liters. And that gets my moles to go away. So I've canceled everything. I'm left with liters of hydrogen. That's what they were asking for in the question. So all I have to do is punch this into the calculator. So when we're doing this, you want to take the 13.5 times 22.4 and you want to divide it by 40.8. And the answer I get is 7.54, and that's going to be liters of hydrogen. I want 3 sig figs because of the 13.5, so this is what I'm going to use as my answer. And that's it. Let's do another. All right, on this one we have nitrogen gas reacts with oxygen to form dinitrogen trioxide. So nitrogen gas, nitrogen is a diatomic, reacts with oxygen. Oxygen's also a diatomic to form dinitrogen trioxide. I need to balance. N's are good, 2 and 3 O's, so I'm going to try and make 6 O's. So I'm going to put a 2 on that side, 3 there, and that means I need 4, so I'll put a 2 in front of there. All right, there's my balanced equation. How many molecules of oxygen? Oh my goodness, we get to use Avogadro's number. So I'm going to put MOLEC, so remember it's molecules, not moles, of oxygen are needed to make 5.5 liters of dinitrogen trioxide at STP. We get to use that wonderful conversion factor again. And away we go. So we want to start with what we're given. 5.5 liters dinitrogen trioxide. I am in liters. So the first thing I'm going to do, that is a terribly unstraight line, is I'm going to use this conversion factor first. So 22.4 liters needs to go on the bottom because I needed to cancel this, is 1 mole. Liter, oh remember this is over 1. Okay, now I can go to the chemical reaction here, and it's balanced, so 2 moles of the dinitrogen trioxide is produced from 3 moles of oxygen. And I need to go to molecules, so that's where we go back with Avogadro's number. We use that guy. So since moles are on top, I put my 1 mole of oxygen on the bottom. And the 6.02 times 10 to the 23rd molecules goes on top, we'll say, of O2. All right, that is the end. We're going to take all this, punch it into the calculator, and see what we get. So 5.5 times 3 times 6.02 times 10 to the 23rd divided by 22.4 divided by 2. And your answer should be 2.2 times 10 to the 23rd molecules of oxygen. And I did 2 significant figures in my answer to match the 2 sig figs from right there. That's your final answer. I think we're going to try one more. All right, so this is the last one, I believe. We'll see if I'm right. Calcium carbonate decomposes. Calcium is a +2, carbonate is -2, so when I put them together, it's just CaCO3. Decomposes is my arrow into calcium oxide. Calcium is +2, oxygen is a -2, and a common gas. All right, well, hold on a second. Let's look at what we've used. We have the calcium taken care of, and we've used an oxygen. We still need to take care of this carbon, and if I think of common gases that include carbon, the one that really pops to mind is carbon dioxide. So this is the formula we're looking for: 3 oxygens, 1 carbon, and a calcium. So there's our balanced equation. It says when 45.5 grams of calcium oxide, so 45.5 grams, are formed, how many liters of gas is also formed? So this was our gas. It wants to know how many liters. And again, we're at STP, so we're going to do that 1 mole equals 22.4 liters. All right, so we're going to start with what's given. The first thing I always do, no matter what, if you're in grams, is to use the periodic table to go to moles. So if I go to the periodic table, I look up calcium and I look up oxygen. I have 1 of each. So 40.08 plus 16 gives you 56.08 grams calcium oxide. Oops, over wood. I always forget that. Then I can use the balanced equation. So for every 1 of these, we have 1 mole of those. So my 1 mole of calcium oxide is 1 mole of carbon dioxide. And I'm not trying to get to grams, I'm trying to get to liters. So I use the conversion factor from STP, that guy up here. So 1 mole of CO2 is 22.4 liters. And that should do it. Everything canceled except my liters of CO2, which is what I was looking for. So I'm going to punch this into the calculator. 45.5 times 22.4 divided by 56.08, and you're going to get 18.17, but if I look back up here, 3 significant figures, so I'm going to say that that is 18.2 liters of CO2. All right, that's it. All right, and just like that, that's the end of podcast 1.2.